integral, this is called the surface integral, and this is called the this is the Green's theorem, this is Gauss's theorem. So del dot gradient of t dot di, if you just integrate from a to b, what are you going to get? See, yesterday we did gradient of t, right? And dot di, what did I get? What did we get? What is that? We obtained this one. We are essentially obtaining this one, right? What is this? This is nothing but a representation of dt, right? Now, if I integrate from 1 to 2 or a to b, what am I supposed to get? A to b dt is tb minus t, right? So if you operate this between a to b, you are going to get what? What is the temperature difference between? So now you see the temperature contour. Say every day in the news you see the temperature variation across the country, right? Now, if you take a dot product with respect, say suppose somebody tells us what is the temperature difference between, say suppose Ranchi and Guwahati. So you have to just get the position vector there. You have to note down the temperature gradient, and then if you take a kind of integral of a to b, you are able to get what is the dt or temperature difference. And temperature difference is mostly this is giving you the driving force for the heat flow, right? So you can really do a three-dimensional analysis of a geometry like this in order to know what is the temperature difference between 2 points A and B to any two arbitrary points. Earlier you were doing this in a one-dimensional mode in a particular coordinate system. Now this gives you including the footprint of all the coordinates to any arbitrary point in a three-dimensional space. Right, you can really extend this entire activity to an n-dimensional space with the types of notations right now you know. The other one is the divergence theorem. What does it say? That this divergence of V, if you take a volume integral of this divergence of V, it is nothing but the cyclic integral of all the fluxes. V dot dA is all the fluxes. V is what? V is a velocity vector which is in an arbitrary direction. If you take a dot product with respect to the A, which is the normal to the surface, so then what you are doing, you are basically taking the component which is in this direction, this direction, this direction, this direction, that direction, that direction. So essentially what you are saying, say if you have a rectangular box and from each surface there is some material that is coming out. So sum of all the fluxes is nothing but the change of the property inside the volume. Right. So this is called the Gauss's divergence theorem. You are very much aware of, and this is Green's theorem. Like say perhaps this is Stokes, this is Gauss, and this is Green's theorem. Green's theorem says that del cross V dot dA is equal to cyclic integral of V dot del dA, V dot di. These are all position vectors. What does this mean? This del cross V is like these small recirculations that are happening inside. So this is a kind of this is the area that you are considering. In that area, these are the spins, these are the rotations. Now, if you do a kind of area integral of that, it is nothing but what? It is nothing but the total surface integral of the whole process, right? Say suppose you want to really, what is the use of this? Say suppose you want to really, you have an atomic structure and you know the electrons are rotating at a particular direction. Say suppose p orbital, d orbital, s orbital, and all. Now you really want to know, say suppose electron is a kind of negatively charged particle, and then there are so many and they are rotating at different directions and different orbitals. Now if you really want to sum up for an atom, right? So you can really do that using this sort of integral process. Or what is the use in say suppose fluid mechanics or heat transfer? Say suppose you have seen the big rivers, right? And there are a lot of swells. So you really want to know how dangerous in terms of the swirling current that is there in a river. So these are all small swirls you can think about, and it is nothing but the summation of the whole process that is happening in the area. So this is the physical significance of the Green's theorem, right? This we have already talked about. This delta is the Kronecker delta. Right, this we discussed in a great detail yesterday. We also talked about the computation symbol, and this is used in cross product, and this comes out in a dot product, right? And then, we were doing this sort of operations. I have just given you some examples. The notation, the way I have used it is a bit different, but then you can really have all these things. You can really, do a little bit of scribbling. Because the quiz will be coming, so I will be asking some questions with this. So just do a kind of activity in terms of your home. Just take up these examples and perform these activities. More or less, whatever is there, I have discussed already with you. Now, say suppose these slides are given just to give you an exercise. Say suppose sigma is a second order tensor and tau is a second order tensor, right? If I add these two, what I am going to get? I have a second order tensor sigma, which is sigma ij, ei ej. And then I have a second order tensor tau, say tau mn, en, right? If I add them, what am I going to get?
Second order tensor.
I'm going to get a second order tensor, right? If I take a dot product between them,
Scalar.
If I take a dot product between two tensors, what am I going to get?
Tensor.
Yes, because eij, emk, two will go into Kronecker delta, other two will survive. This will be a tensor, right? If I take a dot product between a second order tensor and a vector, what should I get?
Vector.
I'm going to get a vector, right? Because eij and ek. So ejk goes to Kronecker delta, ei remains. If I take a cross product between a tensor and a vector, what should I get?
Tensor.
So eij cross, ek, right? Now, when you get a cross, you are going to get a vector out of it. I mean, you are say suppose you have jk, so you are going to get em, right? And ei remains. So ei diadic em means it is going to remain as a tensor, right? So if you take a dot product of a tensor with a vector, you will get a vector. If you take a cross product with a tensor, you are going to get a tensor. If you take a dot product between the two tensors, you are going to get what? You are going to get tensor, right? So you can see that a lot of permutations, combinations are possible here. This we have already discussed. Say suppose I have a velocity vector v and I take a gradient of that. What should I get here?
Scalar.
Gradient.
Tensor.
Yes. Divergence leads to scalar, right? If I take a gradient, so del xi ei vj ej, so that means del vj del xi ei ej, right? So you will get, a tensor quantity here, correct? If I take a divergence of a tensor, what should I get?
Scalar.
Divergence of a tensor is leading to what? Divergence of a tensor will lead to a vector, yes, because ei ej and then I have ek for the del x. Now this ek and ei will collapse to a Kronecker delta and I will have ej, right? So you must do, all these things are given here. I just did not use the summation symbol. You can make use of the summation symbol also and do practice all the examples are given, right? So many examples are given, and in the quiz typically I ask, like, I'll pick up one and I ask you to answer one of those questions. So typically I take the quiz from the lecture notes, so that's why you should go through them very, very carefully. Okay, now once we are through with that, then we have now created a mathematical platform in order to study the heat transfer, which is a part of our classical mechanics. Okay, once you understand classical mechanics, you have to graduate to quantum mechanics. Once you understand quantum mechanics, you have to really look at the special relativity before you go for the quantum field theory. So if you understand these four, you are essentially having most of the fundamental background related to the modeling, the conceptual aspects of different types of phenomena that is happening around you, right? And whatever we are going to operate here, it is all in the Newtonian mechanics domain, and these three will be excluded for the time being, because first we have to have a foundation here, and then only we can go to the other aspects. Now, in order to really have a hold on the Newtonian mechanics, you need to understand a few types of differentials. Okay, so let me just do this part for you. That let's say suppose yes. So suppose I say that there is a scalar phi, and phi is a function of what? Phi is a function of t, x, y, z. You see, now I have complicated the matter a little bit. Then I have introduced the spatio-temporal. So this is associated with the space, and this is associated with the time. Overall, this is called the spatio-temporal variation of a scalar, say suppose phi, right? So if I write d phi, can anybody prompt me what will be my right hand side here? Yes, quickly.
Del phi by dt into dou dt.
Del phi by
del t.
Del t. What is constant here?
In all others, x, y, and z.
Okay, this is into dt, right?
Yes.
Then
del phi by del x.
What is constant here?
Ty and z.
This is dx, right? Then
del phi by del y.
What is constant here?
dxz.
And dy. Then I have
del phi by del z. Dxy and then dz. Right? Yes.
Now, in this sort of situation, if I really divide the entire matter with this, right? So what am I doing? I'm dividing the entire space. That means I'm trying to define d phi by dt. You note that this has become d phi by dt is equal to what? Del phi by del t. I don't write those constants now. Plus, what will happen to my this term? Anybody?
Dt.
Yes. So what is that?
X coordinate of velocity.
Yes, I can write either Vx or say let us write Vx. X component of velocity, right? Vx yes. Del phi by del x, right? Because this dx by dt is going to be Vx. Then what will be my next term?
Vy into del phi by del y.
Then
Vz into del phi by del z.
Right. So now you see the variation that I was looking for, variation of phi any scalar. This phi can be temperature, this phi can be pressure, this phi can be concentration, this phi can be any scalar. Even x directional velocity, y directional velocity in a vector, these are also scalar components, right? So you can really see that now the variation, if I really want to know what is the spatio-temporal variation of phi, it is an addition of all the four components, right? And exactly this is what you see here. Say suppose this is written in terms of C. So dc by dt is nothing but this, which can be written. This is what I derived just now. C is a scalar phi, and this dc by dt can be written as. So here what I can do, I can write this as this is equal to. This is equal to what should I write? Del phi by del t plus what I can write here. This one. This v is a vector, right? Now I'm writing in the vector form, and then what I should write here? What will be the next term I have? Quickly, yesterday we derived
gradient of phi. Gradient of phi.
Gradient of phi. Fantastic. Gradient of phi, right? So this particular thing is called the substantial derivative, or d phi by dt. So what am I doing here? You just see that how exactly I'm looking at that. See, this is a kind of differential. Differential means I'm just looking at how phi is changing with respect to time. What is that? This is called, say suppose if I fix a particular point, a location, I fix a particular location and I see how phi is changing with respect to time. Whereas these three components are, I am fixing a particular time. I am looking at a particular time how it is varying with respect to space. All these three terms are doing that. So there is a difference. There is a big difference between this term and these terms, right? There's a difference here. What is constant here? Here constant is time. What is constant here? Here constant is the space, that is x, y, and z. So this particular term in general is termed as a local variation, right? At a particular location, what is the variation, right? And this particular thing is called what? This is called the spatial variation, right? Now, if you really create a situation where, say, suppose you have a static fluid, you have a bottle filled with water. What will happen to this term? Anybody? If there is a
Zero.
static, this will be zero, right? Because Vx is zero, Vy is zero, Vz is zero, right? So if there is a static, if there is no fluid flow, if there is no motion, this particular term will be zero, the spatial term. Phi by del t, the partial derivative, right? So in general, these two terms are divided as, this is called the local term, and this particular thing is called the convective term. Convective or advective, there are two terminologies that are used in general, right? So this is an advective term. Okay. Convected means what? Suppose there is a flow. Suppose Brahmaputra river is flowing, or river Ganges is flowing, and say suppose if you put something on top of that particular object, say suppose if you have a boat, even if you don't start the boat, if the river is flowing, the boat is also going to flow. That is what you have brought in with this Vx, Vy, and Vz, right? And it is true for anything. It is true for concentration. It is true for temperature. It is true for any variable that you really look forward. So you have basically three types of derivatives in Newtonian mechanics. One is called the partial derivative. What is a partial derivative? If you fix all the other variables and look for a particular variable, how is the change? So what is the feeling? Suppose we stand on a bridge and observe the concentration of fish just below the bridge as a function of time. Say I am looking at a particular point, and at that point I want to see how many fishes are there with respect to time. That is your d phi by dt. What is total derivative? Now suppose we jump into a motorboat, speed around the river, sometimes going upstream, sometimes going downstream, sometimes across the current. All the time we are observing the fish concentration at a particular point, right? Not only at a particular point, at every point rather. Okay, so that is your total derivative d by dt. Whereas what is substantial derivative? Next, we just float along the current and observing the fish concentration, right? So this particular dc by dt is called the substantial derivative, and you will find this is very, very important in terms of modeling any type of Newtonian mechanics, right? What is Newton's second law, by the way? Can anybody tell me what is Newton's second law? Yes, quickly. What is Newton's second law? Quickly. Force equal to mass into acceleration, right? Am I correct? So now, say suppose I have written rho, which is density, and dv by dt. Okay, What is v here? V is the velocity vector, right? So dv by dt is what? dv by dt is what? Yes. So dv by dt is your acceleration, right? And if I multiply with rho means what is this parameter turned out to be?
Force.
Force or force per unit?
Per unit
Volume.
volume.
Volume, right? Now say suppose I write this way rho. So dv by dt I just now derived. What is that? Del v by del t plus what is that? V dot del v, correct? Am I correct? Just now we did,
Yes.
right? Say I have just replaced the scalar with v here. So you just did that. This is v dot del v. This is v, this is v. I'm just replacing these three things, right? Now you tell me what is the unit of this? What is the unit of this? Let me just expand the thing for you. It will be much easier for you. See, what does it mean? This means that del v by del t. Say suppose I'm writing only x component, del u by del t plus, sorry. Let me just discard this. I'll come back here. So what am I writing? I'm writing rho into dv by dt, which is equal to rho into del v by del t plus v dot gradient of So what I'm trying to write is something like this: rho into dv by dt equal to rho into del v by del t plus v dot gradient of v, right? This means what? Rho del v by del t plus u into v dot del v is what? V dot del v will be into, basically this will have three equations. So if I write in terms of u only del u by del t, this will be u into del u by del x plus v into del u by del y plus w into del u by del z, right? This is my x component. So essentially this means there are three equations. What will be the second equation? See, del v by del t plus u into del v by del x plus v into del v by del y plus w into del v by del z, right? So these are all vectors. Just to differentiate the v with the cap is a vector and v with non-cap is a scalar. Del w by del t plus u into del w by del x plus v into del w by del y plus w into del w by del z. So essentially, if I write like this, if I'm writing like this, I'm essentially looking for a cryptic notation for all this. Now, what is the unit of this particular component? What is the unit of this particular component? Can anybody tell me what is the unit of this particular component? Del v by del t.
Meter per second square.
Meter
So
per second.
what is this term?
Acceleration.
Acceleration. Now what is this term?
Instantaneous velocity.
If this is acceleration, what it should be?
Instantaneous acceleration.
Huh?
Instantaneous
Acceleration.
acceleration.
What is that? Repeat. Say suppose you take u, right? U del u by del x. Okay. What is the unit of this?
LT minus 2, same as acceleration.
So what is this? This has a unit of acceleration. This also has a unit of acceleration, right? So what is this? Anybody? So both the terms are accelerations. Okay, so that's where the differentiation is created now. Why am I writing this? Because just to tell you that up to this point you are very comfortable in telling that if I'm really looking for a kind of Newton's second law, force equal to mass into acceleration. I really did not differentiate between two different types of acceleration. Say, suppose if this is v, del v by del t, here x, y, z is constant. So this is called the local acceleration. Whereas this is associated with the acceleration associated with the flow of the fluid. That is called the convective acceleration or advective acceleration. If you have a medium, and if the medium is making flow, and that flow is leading to an acceleration, that is called the convective acceleration. Whereas if you just fix at a particular point and if you start looking at the change in the velocity, that is called the local acceleration. So in a Newtonian mechanics, you just have to consider the local as well as the convective acceleration, right? And that comes from the most fundamental equation. I did not do anything. There is no assumption here. I just started with like a particular variable that is a function of the space, that is x, y, z, and the time, that is t. You can take r theta phi, you can take r theta z, you take any coordinate system, you just place the coordinate system, and then you look for the variation, which is the derivative of that particular variable. It can be temperature, it can be concentration, it can be any of the velocity components. So it will lead to what? It is going to give you a derivative which is called the substantial derivative or total derivative. What does it measure? It measures the local variation with respect to time with the convective variation with respect to time. Okay, great. Convective variation at a particular time. Sorry. Great. Once we are done with that, we are more or less through. We just now have to understand. So what type of equation is this, by the way? Can anybody tell me what is this equation? In mathematical term, what type of equation is this? It's an algebraic equation, differential equation. What type of equation is this?
Differential equation.
What type of differential equation is this?
Partial.
It's a partial differential equation, right? So just to give you an idea, what is an ordinary differential equation? Can anybody tell me? What is an ODE, ordinary differential equation?
In which we take the full derivative in terms of some quantity without keeping
an
anything constant.
ODE involves an unknown function, that means a dependent variable, okay, and its derivatives, right? An unknown function y and its derivatives, that is called an ODE, right? What is a linear ODE? What is a linear ODE and what is a non-linear ODE? Any idea?
In linear ODE, we have powers of derivative as 1.
Yes.
And in linear derivatives, we have
non-linear
powers derivative as greater than 1.
No, non-linear derivative is when the coefficients are the functions of the independent variable. Okay. Yeah. Now, this is a typical partial. This is a typical partial differential equation. What is the order of this partial differential equation? Can anybody tell me? What is the order of this equation? Second order.
2.
Right? Is it linear or non-linear?
Linear.
Linear.
If the function, if a, b, c, all these coefficients are functions of x and y, which is the independent variable, it is linear. If it is the function of phi, which is the dependent variable, then it is not linear. Okay. Now, this is the typical form of an ODE, right? Now, PDE can be of different types. If I write a second order PDE like this in an equation form, if these coefficients, if b square minus 4ac is greater than 0, this PDE is called a hyperbolic. B square minus 4ac equal to 0, that is called a parabolic. And b square minus 4ac less than 0 is called elliptic. Just remember, it has nothing to do with hyperbola. It has nothing to do with parabola. It has nothing to do with ellipse. Okay, there is no geometrical connection, only because, by definition, it matches like this. These are all these conic sections that we studied in coordinate geometry. It just matches like that. That's the reason why they have terminology, why the terminology is taken like this. Right? Now, say suppose I give you a situation. Suppose I give you a situation with this formula that say del square phi by del x square phi by del y square equal to 0. Essentially, I am telling you a Laplacian. Now, what type of equation will be this? Can you quickly calculate from this? Del square phi by del x square plus del square phi by del y square equal to 0. What is my b here? How much is b here?
0.
0, right? How much is a?
1.
1. How much is c?
1.
So what is b square minus 4ac?
-4.
So what type of equation is this?
Elliptic.
It's an elliptic equation, right? So similarly, see, you will see I have given all the examples. So this equation is an elliptic equation, which is called you also know this is particular thing is called the Laplace equation, right? If you in the right hand side, if you have a constant, say suppose r or rho, that is called the Poisson's equations. These are all elliptic equations. By the way, how many boundary conditions do I require to solve this problem? This particular differential equation, if I want to solve, how many boundary conditions do I require? Anybody has any idea?
2.
How come? It is second order in x and second order in y, right? So how many boundary conditions do you require? It's a two-dimensional equation, right? How many boundary conditions do you require?
4.
4 boundary conditions you require, right? You need 2
Yes.
boundary conditions in x and 2. See what the order of an ODE determines how many boundary conditions do I require. As many times I integrate, I need 1 boundary condition in order to get rid of the constant, right? So here I require 2 boundary conditions in x and 2 boundary conditions in y in order to really get a solution. Correct? Now this is called a if you have this sort of equation, this is a parabolic equation. So del phi by del t equal to alpha del square phi by del x square. You will find, we will do this, heat conduction del t by del t, del capital T by del small t equal to alpha into del square t by del x square. So if you put those coefficients, you will find that it will become, b square minus 4ac is equal to 0. Now, what is the order of this equation? Can anybody tell me what is the order of this equation? What is the order? Yeah. 2. It's a second order in space and first order in time. Okay. Because now you have to differentiate between space and time, correct? How many boundary conditions do you require?
3. 3.
Why 3?
2 in space, 1 with time.
2 in space and 1 in time, right? So in the time case, you don't call it a boundary condition. You call it as an initial condition, okay? So you require 1 initial condition, the condition at time t equal to 0, right? And then you require 2 boundary conditions in x. So 1 initial condition and 2 boundary conditions is going to give you the solution, right? And this is basically unsteady heat conduction equations. You will find later it will come up. So this is a parabolic equation, and this is a hyperbolic equation. So we'll for the time being, this is not coming on our way. So we are going to avoid this, right? Great. So what are the governing equations in Newtonian mechanics? I have to really take care of mass conservation, momentum conservation. By the way, what is the second law of Newtonian mechanics? Can anybody tell me what is the second law? Newton's second law, can anybody tell me? Yes, quickly, somebody. There's a confusion, there is a doubt that I'm going to really clear here. It's important that you speak up here. Otherwise, I will not be able to convey it properly. Whatever is there in your mind, you tell me. Initiate the
Force is equal
discussion.
to dp by dt.
But what is the statement? Is it force is the statement? Newton's second law? Force is the
Force
statement?
is directly proportional to rate of change of momentum.
Rate of change of momentum. What type of momentum? Do you know what are the different varieties of momentum?
So here it is linear momentum, probably. Like,
is it linear momentum? In Newton's second law, whether it is linear momentum or angular momentum? Linear.
Linear momentum, sir.
So what happens to the angular momentum? Why not angular momentum? Why only linear momentum? So the doubt here is, what type of momentum, and it is the total momentum. Okay, this is where people confuse it, and I'm going to really prove you that that is the case. So it is the total momentum that is taken into account. Linear, angular, both. It's basically a kind of you are going for a kind of conservation of momentum. So what are the conservation laws of physics? First, you conserve mass, then you conserve momentum, then the conservation of momentum leads to force balance. The conservation of linear and angular momentum leads to force balance. That we are going to discuss. Then you have the energy conservation, right? And the medium needed to be the continuum. Continuum, what is the definition of continuum? Say, suppose when I say that del phi by del x, what is the inherent assumption here associated with phi? The assumption is that phi is a continuous function. Phi is not a discontinuous function. Phi has a solution for every point in the space. Nowhere it is diverging. If it diverges, then this equation doesn't hold good. Then you need to look for the stochastic solutions or the probabilistic solutions. So the first assumption that we make that when I'm solving for temperature or concentration or velocity and anything, we assume the variable to be constant, to be continuous, right? And in a medium, all the properties are continuous. That medium is called the continuum. We know that, say, suppose if I take a water, a cup of water, there are water molecules, and in between there are vacant spaces. But in case when we really do the continuum mechanics, we assume that it's a continuous phase. There is no discrete phase, and that is what is called the concept of the continuum. Anything larger than 1 millimeter, that's the reason why all these conservation laws, they hold good, right? And then you see that I have silently written here that I did not write that entropy conservation. I write entropy balance. Why? Because entropy is one parameter which you cannot conserve due to the irreversibility of the engineering processes. So what you do, you just balance it and see how much entropy you have generated, which is the measure of your loss. So if you understand all these things together, then you are through with the engineering principles of different types of motions, different types of engineering processes, so on and so forth, right? Yes. So let us start this part, because ultimately this is going to take us to the simplest possible form, which is called the heat conduction equation. So everything starts with a particular theorem. It's called Reynolds transport theorem. If you understand this, you understand the entire Newtonian mechanics, right? So do you have any doubt in this particular term, d phi by dt? Anybody has now any doubt in this term d phi by dt? What is this d capital phi by dt? Anybody explains me what is this? We are just studying for last 45 minutes. Yeah, what is this? d phi by dt is what? Somebody. Just now we did, right? What is d phi by dt? What is capital D? Capital D is the substantial derivative, right? Yes. Please tell. Anybody wants to speak up? What is this d phi by dt? Just now we did, right? What happened?
Sir, it represents the total change in the phi with respect to time.
This is called substantial derivative, right? Just now we discussed what is the total change of phi. What are the components of the total change?
Local and connective.
Convective. Convective.
Yes.
Or advective, right? So if I really look for any property, say suppose mass, momentum, energy, any property, right? Entropy, any property, if I look for a change, this is the total change with respect to time and space. I have just calculated these things, right? This is the total change with respect to time and space. We have just calculated this, right? From the basic, equations, right? I did not make any assumption here up to this point. Now, Reynold transport theorem says that rate of increase of the property in the system. This is the change of property in the system, right? What is that? It's a summation of two components. One is rate of increase of the property in the control volume. Say suppose you take a very small differential volume. Suppose phi is the mass. You take a small volume dV and you measure what is the amount of mass that has increased here, right? And then what you do, you just integrate over the entire volume. So you think about this is per unit mass. Capital phi is an extensive property here, which includes the total amount. Small phi is this capital phi divided by m. Small phi is the amount of the property per unit mass, right? So for a differential volume element dV, rho into phi gives me what? What is the total amount of phi that is changed here, right? Over a period of time, that is del by del t. So del t of cyclic of the volume integral of rho phi dV gives me what? Rate of increase of the property in the control volume. This is one way of change of property. So what is the total spatiotemporal change of the property phi? This is the volumetric change. And the other possibility is that it has a lot of boundaries. Through the boundaries, a lot of things are going out. So something is coming in, something is going out, for an open system. So what I do, I say that the rate of efflux of the property across the control volume boundary. So V dot N dA gives me what is the flux that is coming. And then if I multiply by rho phi and take a surface integral, that gives me what? That gives me the total amount of this property phi, which is going through these different surfaces, going either coming in or going out. So essentially what I'm saying that if I consider a control volume element, the change of property in this control volume element can be the summation of what? What is the change with respect to time over a period of time in the control volume, and what are the fluxes, total amount of fluxes across the space. Right? It looks a little bit, a little bit like, out of the box, but then, you see that it will be very easy. Say, suppose I'm looking for phi is equal to mass, right? So what will be my capital phi for mass? What will be my capital phi for mass? Can anybody tell me? Quickly. What is my capital phi for mass? It's m, right? And what will be my dm dt for a process? Anybody? What is my change of mass with respect to time?
0.
Zero. Right? Because, other than these nuclear reactions, somewhere you are going towards the light, velocity of light. There only there is a changeover of mass from mass to energy, right? Otherwise, mass doesn't change. So d phi by dt for mass will be 0. What will be my small phi? Can anybody tell me? What is small phi? Small phi is per unit mass, right? So what is my small phi? Small phi is 1, right? So if I put small phi to be 1 here, if I put small phi to be 1 here, this is my Reynold transport equation. That Reynold transport equation modified to what? Reynolds transport equation modified to this equation. Sorry, Reynolds transport equation modified to this equation, right? Now, if I apply Gauss's divergence theorem, what is that? We just read it. What is Gauss's divergence theorem? We just have gone through it. So V dot dA is divergence of V d tau, right? Surface integral all fluxes V dot dA is equal to divergence of V tau. So if I apply Gauss divergence theorem, I have given all the steps to you. Now V dot, this is NdA, means dA vector. Now if I convert this, then this will become what? Del dot rho V, right? Del dot rho V dV and rho dV. Now, if since both are now volume integral, if I just take into the volume integral, what happens? This becomes del rho by del T, del dot rho V dV is equal to 0, which is leading to what? My mass balance equation, or we call this as a kind of like the very famous mass balance equation. What is that? Del rho by del T plus divergence of rho V is equal to 0. Now, if rho is constant, then you can write what? Divergence of V equal to 0. That means this is your continuity equation for what? Incompressible fluid. Rho equal to constant means it's an incompressible fluid, right? Incompressible means the density is not changing with respect to time and space. But this is the total mass balance equation, right? And at the end of the day, you are already deriving this equation in your fluid mechanics classes. So you can see that del dot rho V, V dot rho, this I have also forgotten. This you can also do here, that if you have del rho by del T plus del dot rho V equal to 0, this you can write as plus rho del dot V plus V dot del rho, right, equal to 0. Now, del rho by del T and V dot del rho can be written as what? D rho by dt. This term and this term, this is the convective term and this is the local term, plus rho divergence of V equal to 0. In this case, if you put rho to constant, then what happens? Then again you require del dot V equal to 0. So this also possible to write. You can write this particular equation also in terms of the substantial derivative. So that is given for, right? Great. Now, say suppose this is related to mass conservation, okay? Sorry. This is related to mass conservation. Now, in case of momentum, what will be my phi? Can anybody tell me, in case of momentum, what will be my phi? Capital phi. What will be my capital phi? What will be my small phi? In case of momentum?
Sir, mv, mass into velocity.
But mass, generally mass is always here, mass per unit volume, right? Because you are anyway going to do volume integral. So momentum comes out to be rho v, right? Okay. Am I clear? So phi you are going to replace as rho v. Is it clear? So here.
Sorry, we divided by V on both sides, like by volume. That's
Yes.
Okay.
Yes. So you put rho and then you divide by volume. Yes, very true. Right. Okay. So if you put rho v here, and then the rho goes away. Why? Because you have got only v per unit mass. Correct?
Yes, sir.
Now, if you do that way, then what happens again? The same formula I use, replace them. And then what happens? Then first I do a kind of this area integral, surface integral to volume integral using divergence theorem. Then I use this, in the divergence theorem, I make use of this, right? So ultimately the entire thing comes out to be what? Of a control volume rho of dV by dt dV. So what is this term? Anybody tells me what is this term? What are these two terms? We can really comprehend rho into dV by dt into dV, cyclic integral of volume of this. So what is this term? Can anybody tell me? This is coming straight away from Reynolds transport theorem. I'm just doing the same set of operations I was doing for the mass balance to get this finally, right? What is this term? Can anybody tell me? Rho is mass per unit volume. dV by dt is my total acceleration. And dV is my control volume. So what is this? In terms of Newton's second law, what is this?
4.
Is it dimensionally force?
Mass into acceleration.
Mass into acceleration.
Right? This is what is MA that you talk about. Okay, and this takes into account, this is true for any geometry. Whatever you did F equal to MA, that was for a one-dimensional, line geometry. This particular equation is true for any geometry, any sphere, rectangle, car, aeroplane, anywhere you can apply. So this is your mass into acceleration, right? And then what is your mass into acceleration coming out to be? Mass into acceleration is coming out to be your force, right? What are the different types of forces possible? There are two types of forces possible. One force is called body force and the other force is called surface force. Okay? Entire types of forces you can divide into two types. One is called a body force and the other is called the surface force. Any example of body force? Can you give me any example of a body force? What is a body force? Anybody knows?
Gravitational force.
Yes. What is a body force?
It acts on every particle of the body.
Yes, but to define it in a much better manner, that if your force is proportional to the mass, that is called a body force. If it has to have a kind of influence of the mass or volume, that is called a body force, like gravity. Apart from gravity, any other body force?
Electrostatic.
Yes, electric field force is a body force. Else?
Then magnetic force.
Magnetic forces, centrifugal forces, all these are body forces. And there are variety of forces which are called surface forces. Any example of surface force?
Surface force has
Friction.
Yeah, friction.
Friction, very good. Friction is a surface force. Then surface tension, right? That is also a surface force, right? So if you take, say, for a body force, force per unit volume, and then rho dV gives you the total force. And for a surface force, force per unit area into the multiplication of the area. So for the volume, that gives you the total surface force. So what you do, you take a surface integral of the surface force, volume integral of the body force, and that is equal nothing but equal to mass into acceleration. So this is your Newton's second law of motion, true for all geometries, where this volume integral and surface integral holds the key for your geometry. Now, if you convert this surface integral into a volume integral, this T can be written as n dot sigma. This you will do in fluid mechanics. So this can be converted into divergence of sigma. This is a vector. This is a vector. Divergence of rho VV. VV is a tensor, but divergence of rho VV is a vector. So entirely this equation is a vector, and this is the Cauchy's equations of motion. If you apply Newton's law of viscosity here, you ultimately get the Navier-Stokes equation. Right? So momentum balance is nothing but, conservation of momentum is nothing but Newton's second law of motion. So first what you do, you start with Reynolds transport theorem. You implement the property phi into the momentum, and then you perform, then you get the definition of the mass into acceleration in terms of the substantial derivative. Then you consider all the surface and body forces, compile them into the volume integral. And then if you enforce the equation into the whole space, you are going to get the Cauchy's equation of motion. And then that can be converted into the Navier-Stokes equation applying the Newton's law of viscosity. Right? Great. We go up to this point and we take up this one in the next class. So I was just thinking we are a little bit behind because we are hitting a lot of discussions. So this Friday, I will take a lecture. Friday and Monday, I will take a lecture. And next Tuesday, I will try to go for a tutorial. Right? I think by then, we will catch up with the pace and syllabus, because these parts were very, very necessary and these were a bit complicated. So I took a little bit of time. I'll take more time Friday on this, on the energy balance. So transport theorem to energy balance. These 3 slides are very important because then it will be very easy for me to really deal with the steady, unsteady conduction and convection. Okay. Yeah. Question you have up to this point? Any question? If not, so let us see you on Friday. Friday will be a regular lecture, and Tuesday we will be having. Next Tuesday we may have the tutorial. Okay. Thank you so much.
I don't have any questions, sir, but today's class was so amazing. Thanks.
What happened? Amazing in terms of what?
Means it was very nice. Means all those mathematics. I liked it a lot.
Okay. Thank you. Yeah.
Yes, sir.